Let's take a look at kind of a mathematical example of this. We'll have our heating curve temperature. On the other side, we'll have heat added. Start off at the solid. Once we get to the melting point, we'll go to a solid to a liquid, but our temperature won't change. And then once it's all melted, the temperature will start to change. And then we'll go from a liquid to a gas. The temperature won't change. And then finally, we'll have a gas where we can heat it continuously. And so some kind of question that you might be asked is, how much energy does it take to turn 10.0 grams of ice at negative 10.0 degrees Celsius into steam at 135.0 degrees Celsius, assuming normal atmospheric conditions. And then you're given some data such as some specific heats. So the specific heat of ice is 2.09 joules per gram degree Celsius. The specific heat of water is equal to 4.184 joules per gram degree Celsius. And then the specific heat of steam is equal to 2.01 joules per gram degrees Celsius. And then you're given the enthalpy of fusion as equal to 6.02 kilojoules per mole. Remember that fusion is just another way of saying melting. And that the delta H of vaporization is equal to 40.7 kilojoules per mole. Right? Note that the delta H of vaporization is much larger than the delta H of fusion. And this is common, and it makes sense. In order for something to fuse, to go from a solid to a liquid, we don't need to break these intermolecular forces. We just need to weaken them up enough to allow the molecules to kind of roll around. Whereas when we go from a liquid to a gas, we need to completely break these intermolecular forces, right? Our molecules go from in contact with one another to being very far apart from one another. And so if we think about this curve, we've kind of got 5 sections of it. We've got this first section of it, this second section where we have a phase transition, then again, another heating part, another phase transition, and then another heating part. For the parts where we have our temperature change, we've already covered that. That's our Q equals MC delta T, right? That's the equation that we need to use there. And then for our phase transitions, that's when we need to use our unit conversions and our delta H of fusion / vaporization. And so you would just do this piece by piece, part by part. Step 1, you're talking about going from negative 10.0 degrees Celsius to 0 degrees Celsius. You would use your Q equals MC delta T and then plug in your values. You have 10 grams of ice. The ice has a specific heat of 2.09 joules per gram degree Celsius. Your delta T here is 10 degrees Celsius because it's the difference between your two temperatures. And your Q here will be equal to 209 joules. But note that your specific heat is in kilojoules, right? So you just have to, you can pick either unit that you want, but you got to keep track of them. Generally, they're going to be written as kilojoules. So this is only equal to 0.209 kilojoules. Then you've got to do the second step of this curve. The second step of this curve is going from that solid to liquid. So that's our enthalpy of fusion. So we start off with our 10.0 grams of water. We convert that into moles using the molar mass. And then once we've got the molar mass, we can use our delta H of fusion, which is 6.02 kilojoules per mole. And then plug and chug away, we get 3.34 kilojoules. And then we move on to step 3. Step 3 is heating our liquid from 0 degrees Celsius to water's boiling point, which is about 100 degrees Celsius. So here we're taking water from 0 degrees Celsius to 100 degrees Celsius. So here again, we have to use our Q equals MC delta T. Our mass is still 10 grams. Our C is now 4.184 joules per gram degree Celsius. And then our delta T is 100 degrees Celsius. Plug that all in. I got 4,184 joules. We'll want to convert that to kilojoules. That way we can add them all up at the end. 4.184 kilojoules. Step 4. In step 4, what's going on is we're vaporizing the liquid. And so we'll need to use our enthalpy of vaporization. So we'll start off with our 10 grams of water, convert that to moles using the molar mass, and then use the enthalpy of vaporization to get a total of 22.6 kilojoules. And you can tell this number is quite large, or quite a good bit bigger than our previous numbers. It really takes a lot of energy to go from a liquid to a gas. And then in the final step, we'll take our gas and we'll heat it to our final temperature, which in this case, the problem tells us 135 degrees Celsius. So here we're taking our steam and we're going from 100 to 135. Here we'll use again our Q equals MC delta T. We still have 10 grams of it. Now our specific heat is 2.01 joules per gram degree Celsius. And then our temperature difference is only at 35 degrees Celsius. Our Q here will then equal to 704 joules, which is equal to 0.704 kilojoules. And then if we think about the total energy, we just have to sum it up. And if I did that correctly, I got 31.0 kilojoules of energy. I sure hope I did that correctly because I don't want to remake this video. Anyways, you can see it's not too difficult of a problem. It's stuff that we've already encountered before. It's just a little bit tedious. So make sure you're keeping track of what you're doing and that you're not making some kind of silly mistake.